Good morning. My name is Professor Niazi. This is Plain Trigonometry. First, we're going to be discussing our syllabus, and that could be found on Canvas. We go here to our Math 1613. We scroll and click on Syllabus. You can find it by clicking here, opening up this Word document. So let's discuss some of the things on this syllabus. And you are expected to review the finer details of the syllabus on your own. Okay, you're in Plain Trigonometry. We meet during this time in this location, and we have synchronous meeting. Just in case you can't make it to class, we will have online recorded meetings. As you can tell right now, this video is being recorded. It'll be downloaded, and then it'll be uploaded once it's over. So I'm gonna have to figure out how I interact with students that are watching this. Maybe there's some Zoom chat that you guys could ask questions live, or maybe you can just record your questions and email them to me. Either way, we'll figure it out. The course description is as it is in the handbook. We have some learning outcomes that you should read. Here's our course materials, our textbook, Trigonometry, 2nd edition, Coburn and Hardlick. Your grade will be determined by these qualifications. Okay. You'll be given homework assignment out of each section. Today we'll be lecturing on section 1.1, and you will have homework based off of it. You'll also be given quizzes every Thursday, except for today. No quiz today. Don't worry about that. But this coming Thursday, be prepared to take a quiz. You notice when our final is scheduled and when we'll meet. Here's a link to my YouTube channel where I have trigonometry solutions and explanations. You can check that out. Here's the policies and guidelines. Okay, and if you're wondering about what our schedule is, this is it today. So we're going to go over the syllabus in section 1.1. Okay, and you can access this document on your own at a later time. So I'm required to take attendance, and I guess I should ask who all is here before we begin real quick. Even better yet, instead of utilizing class time to do that, what I can do is pass around a sheet of paper and have you guys sign that with your names. Please make it legible so that I can record your presence today in class. You can start it here and you can pass it around. All right, now let us get to the fun stuff. The mathematics, the trigonometry, all of the formalities are out of the way. Okay, so trigonometry has the word triangle in it, but you, in your study, will realize in this class that triangles are just a mere tool we utilize to parameterize aspects of a circle, namely the x and y coordinate projections of a circle at various angles. None of that stuff might mean anything to you yet, but soon it will mean something to you. But initially, our study is going to be talking about 2 points in two-dimensional space. Mathematicians refer to this as R2. Really, it just means a plane, two-dimensional space, like a board here. So let's say I have 2 points. I have a point in space A. I have a point in space B. All right. A point is a dot. It's literally what it sounds like. Okay. And we connect these 2 dots with something called a ray. A ray is a line that emanates from one point to another point, and it radiates infinitesimally. One last key thing that I forgot on the syllabus, that I did not mention on the syllabus, is my technology policy. Thankfully, I don't see anybody with cell phones out right now, but if you do have cell phones with you, I encourage you to put them on silent or on vibrate immediately. You can take some time and do that right now. I do not allow cell phones out during class for any reason. If you have to talk to a loved one or answer an important message, please get up and do so outside, but technology is not allowed in class. Okay, so this line is called a ray. It starts at one point and it emanates towards a direction infinitely. Okay, so what you can do is you can have a ray going this way, but you can also have a ray going this way. And, you know, for instance, we can have it going through some point C. Notice that whenever you have 2 rays intersecting at a common point, we can define a measurement called an angle. Basically, it's how much does this line deviate from the other line? How much does one line deviate from another line? If this line and that line were the same line and they just lied on top of each other, clearly the deviation would be 0. So we say the angle is 0. But for non-zero angles, we say this angle theta. Angles are usually denoted by the Greek letter theta. We say that this angle has non-zero value. Okay. The study of trigonometry has a lot to do with angles and their properties with regards to circles and triangles. One more point that I want to make here is that this point where the angle is defined at is called the vertex. So whenever you have 2 rays meeting at a common point, it's called a vertex. These are terms we'll be utilizing on a daily basis in this class. Okay? Now, a lot of this stuff you've seen before, most likely in your education prior to this class. And here's some more stuff that you've most likely seen before. But I encourage you to stay very focused because I expect the utmost amount of focus and professionalism from my students. But I do want you to have fun. I want to make math really fun. I want to show you a side of mathematics that you have not seen before, because usually when you get taught mathematics, nobody really explains why. They just say, learn this, and don't really ask why it's true. But in this class and in all math classes, you should have justification for why the things are being said, okay? I will provide 100% justification for why in this class. At this point, I'm just making definitions, so I don't have to say why yet. This is called a ray. I could have called it a may. It doesn't matter. It's just a definition. For now, there is no justification required, but we will get there, and you will get full justification. And any questions and all questions that you have, please ask them. It is, in my humble opinion, that there's no such thing as a stupid question. And that's due to the fact that if you are questioning, that implies that you have intellect. Those who do not question, they may still be intelligent, but the absence of questioning is what might really make you think, what's going on here? So ask away. I love questions. Make sure that if you have any questions, but let's say you're too shy in class, Write them down and email me or ask them during office hours. Okay? I truly want all of you to learn and be successful and to enjoy mathematics. Something that you may think is impossible. I'm going to make it possible. Okay? Now, let's define some special angles. One such special angle is called a right angle. This is when theta is equal to what? 90. Yes, very good. 90 degrees. By 90, what do you mean? And by degrees, what do you mean? Who here can explain to me the concept of a degree? That's all right. Well, I'll explain it to you. A degree is merely a way of quantifying an angle, right? It's a way of measuring angles, just like miles is a way of measuring distance. Just like pounds is a way of measuring weight, okay? So 1 degree is equal to 1 over 3/60th of a revolution. Who can tell me what a revolution is?
A full cycle.
Yeah, a full spin, a full circle. I do not have much room up in here, or else I would do a 360 round kick and show you a revolution. I guess I can make some room over here. Push this over here. Okay, here we go. Oh, well, I'll pick that up in a second. How many revolutions did I just do? 2. So how many degrees would that be? Pardon me? 720. How did you get that number?
Multiply 360 by 2.
Yeah, very good. I should probably return this to its original position. There we go. You guys didn't think math would be exciting, did you? Math is very exciting. I'm going to make it exciting and accessible, okay? Many people, when we talk about math, they're like, oh, I hate math. I was one of them. Growing up, my teachers wouldn't explain to me why, you know, like the area of a triangle is 1/2 base times height. I'd be like, teacher, why? They'd be like, that's just the formula. And I'd be like, teacher, why is that the formula? Who came up with it and how did they come up with it and what's the justification for it? And it's just the formula. Shut up. No, you go into the principal's office. It's not cool. You should justify something that you're trying to explain to someone. So in this class, none of that will happen. You will get 100% justification for why. Again, we have not gotten there yet. Right now, we're just defining things. So what about an acute angle? Acute angle. What is theta equal to here?
Is it anywhere lower than 45 degrees?
Close, very close. Anything lower than 90 degrees. Yes, very good. Very good, everybody. Theta has got to be less than 90. And technically, it has to be greater than 0. Okay, it has to range between 0 and 90, right? Now let's talk about an obtuse angle. Note to self, do not do 360 roundhouse kicks with glasses on. I'm a little on contact lenses. Should probably have worn those today for Trig. I love doing the 360 roundhouse kick on Trig because we talked about revolutions. And it's an exciting way to combine martial arts and athleticism with mathleticism. Okay. Now, this obtuse definition, where does theta range in an obtuse angle?
Greater than 90, but less than 180.
Very good. Very, very, very good. That's right. What would it be if it was at 180?
Be a line.
Yeah, just make a straight line. Okay? So it's not really an angle anymore. I mean, it is an angle. It's 180 degrees. But you get what I'm saying. It doesn't look like this thing where it's like a wedge. It's just a straight line. Okay? Now, more definitions here. Unfortunately, to get to the cool stuff, we have to make a lot of definitions. Because, you know, definitions are like the words to a language. First, you have to have a vocabulary, and then you have to learn the grammar, and then you can start speaking the language. So first, we're establishing the vocabulary of trigonometry. Now, yeah, we discussed that theta is equal to 180. Line. Now, we say two angles, alpha plus theta, if they equal 90 degrees, we call alpha and theta complementary. And if alpha plus theta is equal to 180 degrees, we say that alpha and theta are supplementary. Okay? I know. I'm falling asleep with you. Definitions, definitions, definitions. You got to get these recorded in your brain so that once I start flying and throwing equations out there, you know what I'm talking about. I'll say a supplementary angle here and here, and you need to know, oh, that means if an angle alpha and an angle theta add up to 180, that they're supplementary angles. So here's an example of a supplementary angle. Let's say this is our theta, and then this would be our alpha. Adding this piece to that piece gives you 180. And, you know, if you need a concrete example, we could say alpha is like 130 degrees. And then what do I have to add to 130 to get 180? Very good. So theta must be 50 degrees, right? And let's say I have a situation where I break apart a right angle into two pieces. Let's call this alpha and this, let's call this a theta and this an alpha. Let's say this is 30 degrees. What must alpha be?
60. Yeah,
because 30 plus 60 is 90. Very good. So these are complementary. These are supplementary. Find the complement. Now we apply. Find the complement of theta is equal to 77 degrees.
13 degrees.
How did you get that answer?
Because it's complementary, it's 90 degrees, and 90 minus 77 is 13.
There we go. Very good. Not only do I want you guys to answer questions, I also want justification. That is perfect. That is really good. That allows both me and your colleagues to understand more. Okay, very good. So this implies the complement is, what did you say, 13? That means 13 degrees. What about the complement of 20 degrees?
70 degrees.
70, why?
Because 70 plus 20 is 90 degrees.
There we go. So now we know how to do complements. Here's another example here. Let's clear up some room. All right, what is the supplement of 1, 2, 3 degrees? 123.
Would be 47 degrees.
47, why?
Because 180 minus 123 is 47 degrees.
There we go. This implies the supplement is 47 degrees. Okay? And let's do, what is the supplement of 180 degrees?
It's 0.
Yes, trick question, right? The angle is already at 180 degrees. When I ask you what is the supplement of an angle, I'm asking you, what more do we need to give to it for it to equal 180? Once it's at 180, we don't need to give it anything else, right? So its supplement would be 0 degrees. That's a trivial example, but it's an example nevertheless. All right. Moving on. We talked about how a degree is 1/360th of a full revolution. Okay. Now, let's talk about minutes and seconds. Okay. So, in 1 degree, we're talking about 180 degrees, 47 degrees. In 1 degree, there is 60 minutes. And this is actually denoted by 60 with a little indentation up there. Why are we doing this? I thought degrees was enough, right? Why are we now starting to chop 1 degree up into smaller pieces? What's the point? What is the point?
Because the clock is a circle. The clock is a circle and it like revolves in a 360 degree angle.
That's a good analogy. Yes, clocks are circles and minutes do relate to clocks. That is a good analogy. Matter of fact, a degree is analogous to an hour, right? There's 60 minutes in an hour, right? A degree is analogous to an hour, but that kind of relates it to a clock, but it doesn't explain why we're even doing this. What's the practical purpose of chopping a degree up into finer pieces? You guys all have pensive looks on your face, which is good. It means you're really thinking about it. Well, it's due to the fact that what if we have a phenomena that's occurring that is smaller than a degree? How would we be able to quantify it? Kind of like, how am I, if I measure this table in miles, that's kind of hard, right? If I measure this table in feet, it's a little easier, correct? What's the difference between 1 foot and 1 mile?
Miles longer.
It's way, way larger in magnitude, right? So we need to create new units of measurement that kind of fine tune what we want to use it for. So in astrophysics, when we want to measure how much is a star deviating every day, okay, in astronomy, what we can do is, what you realize is actually a degree is not enough. A degree is too much. The changes are very small. And so we invent a new concept. We say, okay, if we got the circle and we chop it up in 360 pieces, that's good, and that gives us the degrees. But let's get that 1 degree and chop it up into 60 pieces. Okay, because I want to be able to quantify finer changes in rotation, finer angles between 2 rays. Does that make sense? Does that make sense why it would be practical?
Yeah.
Very good. Awesome. Okay, let me define another thing. Guess how many minutes? Guess how many seconds are in a minute? Yeah, it is quite analogous, as this young man pointed out, to a clock. So you get 60 seconds, which we typically denote this as something like that. Now we have a powerful tool. We can describe very small changes in a rotation. That is why this stuff is useful. Now, I get it, Professor Niazi, it's useful. How's it going to help you guys out in your class? Well, you'll be expected to convert between a situation like this. Let's say we have 30 degrees, 15 minutes, and 20 seconds. You'll be asked to convert this to a degree decimal. Okay, what do I mean by that? I mean, like, you know, a degree decimal is like 3.14 degrees. Right now, our degrees is a whole number with some other stuff. But we want to get to a decimal representation of the degrees. Okay? So what we can do is utilize what we know here about the conversion between degrees to minutes and minutes to seconds. Before I go and dive into the calculations, now we're finally doing mathematics with calculations. We've got past the definitions. Before I dive in, I first want to show you something about conversions. Let's take this equation right here. If I set this piece equal to this piece, which they are equal, I get 0 degrees is equal to 60 minutes. What happens if I divide both sides by 1 degree? Divide this by 1 degree, divide this by 1 degree. This implies I get the number 1, because the units cancel. The number 1, the pure number 1, there's no units associated to it. This is equal to 60 minutes over 1 degree. So the number 1 is equivalent to 60 minutes over a degree. Remember that. Furthermore, let's start out with that original equation that we've been talking about. And now, conversely, let us divide by 60 minutes. Both sides by 60 minutes. Oh, 60 minutes, 60 minutes. This implies I get the number 1, the pure number 1. You guys seeing that at home? The pure number 1 is equal to 1 degree divided by 60 minutes. Professor Niazi, this is trivial. These calculations are trivial. Why are you showing us these calculations? You will see why here in a second. All right. Furthermore, you could do the same thing with these equations right here. 1 minute equaling 60 seconds. That implies 1 is equal to 60 seconds over a minute. And it's also a minute over 60 seconds. You get that 1 is equivalent to that as well. So I just skipped the calculations. It's the same thing here. You divide both sides by 60 minutes. You get a 1 here, and you get 1. You divide both sides by 60 seconds. You get a 1 here. Then you would get 1 minute over 60 seconds is equal to the pure number 1, no units. And then conversely, divide both sides by a minute. You'd get 1 over here, and you get 60 seconds over 1 minute. Is that making sense so far? What is 3 divided by 3? 1. What is 17 divided by 17? There you go. So that's kind of cool. Now, what is 1 times any number? Itself, right? 1 times anything is just that number you multiply it times, right? Keep that in mind when we do this calculation right here. Let's delete this information. We've already talked about it extensively. Also, if I erase something that you haven't written down yet, everything, I've calibrated the board here. So everything that I write down will be on the video uploaded shortly after class. So even if you miss something, you can look it up on the video. Like, oh, I didn't get to write that part down, so I'm going to look it up. Okay. If I erase something you haven't recorded yet. Let's convert this right here, 30 degrees, 15 minutes, and 20 seconds into decimals. What we do is we realize that if I want to convert it into a decimal degrees, the 30 part we leave alone. It's already in degrees. Let us start to deconstruct what this 50 minutes is. In 15 minutes, how many degrees do I have? Well, there's a cool, nifty way of finding that out using these equations that we've derived. Notice these guys are just all fancy number ones, right? Fancy number ones. Notice that 1 times anything is itself, right? So if I were to multiply any of these equations times this expression, I could just write equals after that. Because it's the same thing. 1 times anything is itself, right? So if I get anything here and multiply it times here, I can say it equals what ends up spitting out of there, right? Because 1 times anything is itself. Therefore, if this side and this side are the same, I can put equals. Now, what's the point? I want to get rid of this unit, the minutes. So what I'm going to use is I'm going to use this equation here because the minutes are in the denominator. Over here, the minutes are in the numerator because technically this is 15 minutes divided by 1. So I want to have this guy cancel that unit out. This unit, I want it to cancel out with this unit. So what I get is in 1 degree, I have 60 minutes, right? So notice now the denominator units will cancel. And what you end up getting is 15 over 60 degrees. What is that?
1/4, which is 90 degrees.
Is what?
90 degrees.
90 degrees?
No, it's
Well, let's talk about the fundamental theorem of arithmetic. It says that any composite number can be broken down to a unique expression of prime numbers. Meaning, I can say 15 is 3 times 5. And I can say 60 is, for instance, 6 times 10, right? And then I can say this is 3 times 5 divided by 6 is really like 2 times 3. So this is 2 times 3 times 5 times 2, because I broke down 10 to 5 times 2. Why am I doing all this weird stuff? It's so I can cancel. Don't forget over here, we have a degrees. I can cancel out this 5. I can cancel out this 3. So really, you get 1 over 2 times 2, which is a 4th. It's a 4th of a degree. So 0.25. Is that what you were saying? I thought you were saying 90 degrees.
yeah, I thought it was too.
Yeah, it's 0.25 degrees. It's like a quarter. 0.25 degrees. That is what 15 minutes is. It's 0.25 degrees. Is that sinking in? This stuff that I do here is due to the fact that I'm a number theorist. My research interests are in geometric number theory. So I'm a mathematician and I break down numbers that are composite into their unique prime factorizations. Really, you could have just been like, well, 15 over 60 is 1 over 4. If you can do that in your head, great. I, as a number theorist, like to break it down like this. Tomato, tomato, potato, patata, it don't matter. Okay, so whatever method you choose. I like this method because it makes me think of geometrical shapes in my head, because numbers to me have geometrical representations and I can play with them in my head and I can rotate them and they make sound effects like I'm kind of a nerd. Okay, all right, we're not done yet. We now have converted this piece to degrees, and I also want to convert this piece to degrees, and I'm going to use my fancy number ones to do so. I'm sure you have been taught how to convert units, but I'm also almost sure that you have not been exposed to this way of thinking, that your conversion is really multiplication by 1, and that's why you can get away with it and put an equal sign. As mathematicians, we aspire to justify everything we do. Any step that I do mathematically, I have to have a valid justification for it. If you do not have that, then you cannot do the step. Woo! I love math. Let's convert this 20 seconds to degrees now. I want to multiply it by a fancy number 1. Which fancy number 1 should I pick? Left or right? I feel like an optometrist. 1 or 2? 2 or 1? 1 or 2?
The one on the right.
Okay, 2.
Yeah.
All right. Very good. Why did you pick that one?
Because it will cancel out the second.
Aha! Very good. You want to cancel this unit out, because remember this 20 is really divided by what?
1.
1. So it's in the where? Is it in the numerator or in the denominator?
The 1?
The 20.
Oh, numerator.
Good. Very good. That's why it cancels out with the denominator here. Okay. So now we get 20 over 60 minutes, which is what? Yeah, I'll let you have this one. I won't break it down into a unique expression of primes. Although breaking that down is 2 times 10, which is really 2 times 2 times 5. Breaking this down, that's really 6 times 10, which is 2 times 3 times 2 times 5. It's just really fun. The numbers become like puzzle pieces or toys that you can play with in your brain. Okay, but we're not done, guys. We want to convert this to a decimal degree. I need to push this one step further and convert it to degrees. So what am I going to multiply it times? A fancy number 1. Really, I deleted it and we can just invent it. Really, I want to know what is in 1 degree, and that's 60 minutes, because a degree is analogous to an hour, right? So we cancel out the units, and now we will have it in degrees. It's going to be 1 over 3 times 60 degrees. I don't have a calculator. We would have to figure out, that's 1 over 120. What is that number going to be here? Can figure it out for you. Calculators are allowed, by the way, but I'm just going to do it. It's 1 divided by 120. Oh, wait, no, 180. 1 divided by 180. That's 0.0055. There we go. Now that we got this, we are done with the problem. But we have to express it correctly. This is going to be 30.025, because this is where the tenths and the hundredths go. But, okay, 25. And then the rest is right here, 55. You can get that in your calculator by saying 0.0055 plus 0.25 plus 30. That will equal that. Bless you. Does that make sense, everybody?
Yeah.
If not, that's okay. We'll talk about it later, and I will elaborate on it. Maybe send me an email. I'll send you some solutions. I'll make some YouTube videos about it. Either way, I will do my best to ensure every single one of you has every opportunity to succeed. Okay. Where's my thingy here? Okay.
So basically, you just add up the numbers at the end to get
Yeah.
the final answer?
Yeah. Yeah. Your degree, your 30 was already in degrees, right?
Yeah.
So we leave it alone until the end. We got to convert that 15 minutes to degrees when we did. It's the 0.25. And then we got to convert that 20 seconds to degrees, which first you got to convert it to minutes, and then you got to convert it to degrees. Okay, very good. Okay, you guys, let's see here. Now, let's go in reverse. Given a decimal, convert it to degrees, minutes, seconds. So I have one ready here. Let's say 22.33 degrees. I have it here so I don't have to calculate stuff. Sometimes I like to invent stuff on the fly, but then I have like 1/180, and that's, even as a number theorist, we don't do arithmetic well. We think more in the abstract. So people think mathematicians are just human calculators. It's not true. Many of the number theorists I know mess up routine calculations all the time. Math is more than just numbers. As you will see, math is a lot about shapes and how do the shapes get quantified into algebraic expressions and whatnot. Yes, numbers are involved, but that's not all there is to it. Okay? Let's convert this to degrees, minutes, and seconds, okay? Notice that this is equivalent to 22 degrees plus 0.33 degrees. Does that make sense?
Yeah.
Good. So we leave the 22 degrees alone, right? Now we start working on that 0.33 degrees. 0.33 degrees. I want to convert this into minutes and seconds. Let's start with minutes. I got an antsy person here. Which fancy number one would you like to multiply this times? And why? Tell me what it is and why, the justification.
Wouldn't it be technically like 60 minutes over 1 degree?
Yes. Not even technically,
Oh,
accurately. Why did you do that?
well, because either way you look at it, 1 degree over 60 minutes, it's the same thing, right?
You're just multiplying times 1.
Yeah.
You're multiplying this 0.33 degrees times 1. So it's just going to equal itself once you're done. See, this is the beauty of mathematics. It seems like you're doing a lot here, but you're really doing nothing at all. It converts the units, but you haven't done anything. You haven't changed that value, but you've changed its mathematical expression in a different unit. So it's like you're touching it without touching it at all. It's like brain surgery, you know? You gotta like cut out a certain portion of the brain without ruining the other portions of the brain.
You can't just solve the degrees as well.
Yes, good point. So now we get 0.33 multiplied times 60 minutes. And thankfully, I've done this calculation. This equals 19.8 minutes. Now, are we done? No, because I want to convert this to degrees, minutes, and seconds. So we notice that this is really 19 minutes plus 0.8 minutes, right? Why am I doing this?
Because we have to break it down as much as we can, right?
Yes, and recall earlier we discussed what was the point of chopping a degree down to a minute, and what was the point of chopping the minute down into a second? It's to get the smaller and smaller details. So that's why we are getting this fraction portion, this decimal portion, I mean. It's because we want to extract smaller and smaller details, okay? So this stays here. We're done with this as we were done with this. Now let's convert the 0.8 minutes into seconds. How do you do that?
Well, we have to cancel out the minutes, so it would be 60 seconds over 1 minute.
Yeah. And it's because of cancellation, correct?
Yes.
Aha. Cancel, cancel. It's a fancy number 1. Anything times 1 is itself. So this is going to be what ends up being over there. Wonderful. And I've done the calculation for y'all. It's 48 seconds. So that implies 22.33 degrees is equivalent to 23 degrees, 19 minutes, 48 seconds. It's okay. It's okay if you feel overwhelmed and it doesn't make sense yet. With hard work and dedication and my expertful explanations and guidance, you can improve. And you can improve as much as you want to improve. I believe the human mind has infinite capacity. And the only thing that we don't achieve is because we didn't figure it out. That the solutions are always there. We just got to figure it out. One of my aspirations is to create a theory of quantum gravitation, which might allow us to travel faster than the speed of light, creating wormholes with exotic matter, opening the wormholes and traveling to different distant galaxies in an instant. That way we could explore different planets and stars and different galaxies. Because, you know, Earth is kind of not doing so hot with all the deforestation and whatnot. So mathematics is really important because it allows you to study physics. And I encourage all of you to take physics classes with Dr. Neuenswander. And actually our survival depends on math. Isn't that cool? Now, let's talk about coterminal angles. Now that we've done this, let's talk about coterminal angles. I said all that fancy schmancy talk and I didn't really explain it. I feel terrible about that. So I'll take a really quick second to explain what I'm talking about. Ignore what's on the paper, just think about the paper. Really, space and time is like a flat sheet of paper, okay? What you exist in right now is called space-time because you're in space, 3 dimensions, 3 spatial dimensions, length, width, and depth, and time is the 4th dimension. So you exist in 4-dimensional space-time embedded in 5-dimensional hyperspace-time as according to Einstein's theory of general relativity. But what that means is we can create a bridge between 2 locations. So let's say you're here in New York, and let's say we're here in Oklahoma. How long would it take to drive there in a car? I don't know. A while. Maybe like, let's guess 20 hours. Okay. That's because you're driving through the paper. You're driving on the paper. You're driving on the paper to the other edge. Geez, that takes time. It takes gas money. It takes paying attention and not driving into a tree. But guess what? If we had a theory of quantum gravity and we understood how to create and sustain wormholes, what we could do is create a bridge, getting New York and Oklahoma City, connecting them and just passing through the bridge, like so. we would travel there instantly through a wormhole. But this requires us to leave our 4 dimensions and enter the 5th dimension, and then go back into the 4th dimension in which we exist in. None of that's going to be on the test, don't worry. It's just for your information. She looks so relieved. She's like, oh my goodness, not going to be on the test. Yeah, no, don't worry about it. This is not a class in general relativity. I just want to make you guys excited about math and all the things that math can do. It is cool, isn't it? New piece of chalk. Let's continue. Now we're going to talk about coterminal angles here. Remember how we had a vertex and we had 2 rays like this, right? And we defined an angle between them. You guys remember that? Okay. Well, we can call this a leg and that a leg. Sometimes you can call it a leg, sometimes you can call it a ray. You know, technically a ray would be with an arrow that emanates towards infinity, and a leg would kind of stop doing that. A leg would just be kind of like this. But, you know, at this point, it's just really semantics, all right? Rays and legs are kind of the same, not really. But let's say we have this situation here. This is called the initial leg. We call this the initial. And we call this the terminal. What does it mean to terminate something?
Like end it.
End it, like the Terminator. Like Arnold Schwarzenegger. Is that a good impression? Very good, thank you. I think I have some chalk in my throat. To terminate means to end something, right? As this young lady pointed out. What's getting terminated here? The initial leg is getting terminated. Take a look. When I get this leg, what if I picked it up, having it still attached to the vertex, and rotated it and put it back down? I terminated the rotation. And that's why it's called the terminal leg. You pick it up, you rotate it, and you put it back down. That's why it's called the terminal leg. This is the initial leg, and then you rotate it, and then you terminate the rotation. So it's called the terminal leg, because the rotation is over. You've ended it. Make sense? More definitions of concepts here. Now that we talk about picking a leg up and rotating it this way or that way, we have to define, you know, positive and negative. Because, let's see, let me get into your frame view. If I am at the origin, I define motions to the right as positive. And if I'm at the origin, I define motions to the left as negative, right? Yeah. So we actually have to do that with rotations. We have to define clockwise rotations and counterclockwise rotations. I'm probably doing that in reverse. Clockwise rotations and counterclockwise rotations. So counterclockwise will be called CCW, and clockwise will be called CW. I'm not writing all that out. This chalk in my hand making the squeaky noises, I'd rather decrease the amount of writing. Okay. Let us define counterclockwise movements as positive angles. It is the standard way mathematicians define rotations and angles. So now we have positive angles if we rotate counterclockwise. And then we'll have what kind of angles if we rotate clockwise? Negative, right? It's the opposite way. Aha. Ha ha. Wow. It's getting nice now. Now we're starting to talk about rotations. This class is really small. I wish I had a bigger class. I would do more 360 roundhouse kicks. It really calls for 360 roundhouse kicks when you talk about rotations, but I can't. It's too cramped up in here. I guess I could box jump this table and do it, but that's just inappropriate. So let's talk about coterminal angles. What does it mean to co? When you put co in front of something, what does it mean? Part of, you know, something like that. Co. Think of words that start with co. Somebody tell me a word that starts with co. Cohabitate, commingle. I don't know, I can't think of any other ones. That's enough. What do those mean when you co? It's associated with, right? Two things are associated with each other. So, what does coterminal mean? Coterminal angles. I'm trying to make you guess the definition that what it's for. Because if you think about it prior to just it be given to you, then the definition makes sense why it is called that, one. Two, it allows you to memorize it easier, right? Because you thought about it and why is this even a thing? So a coterminal angle is an angle that starting with an initial leg, it lands in the same spot. Here's an example. Let's say, here's my initial leg. Okay, let's say I rotate 90 degrees, okay, to this terminal leg. That's positive 90 degrees, right? Because I did a counterclockwise rotation. Very good. Now, notice I could arrive at the same exact spot utilizing a clockwise rotation. How much would I have to rotate clockwise? First of all, it would be a negative number.
Negative 270.
How'd you get that number?
Because it's a full turn is 360 degrees, and
Okay.
360 minus 90 is 270.
There you go. Does that make sense? These are coterminal angles. 90 degrees and negative 270 degrees are coterminal. Because they terminate at the same spot. Right?
Yeah.
Someone give me another set of coterminal angles.
180 and negative 180.
Yeah. Let's say I rotated like this, positive rotation, because it's counterclockwise, positive 180. And let me note, this is initial, and this is terminal. But as this young man pointed out, you could also rotate the other way, negative 180. And they both land in the same spot. You guys see that? This was the initial spot. We picked it up and rotated it, 180, it landed here. Picked it up and rotated it, negative 180, landed here. They terminate in the same spot. So they are coterminal. Who here has seen that movie? Terminator. One person, too few people. It's supposed to be famous. I haven't really seen it. I ain't seen all of it. Seen bits and pieces. But it's a funny way to relate it to the masses, if you will. Okay. You will be expected, given an angle, to find coterminal angles. Find two positive and two negative coterminal angles to let's say 33 degrees. So here's a situation. Initial rotated positive 33 degrees. And here's our terminal. Now, find two positive and two negative distinct coterminal angles to 33 degrees. Any suggestions?
Then you add 360 degrees to arrive at the same place. And then just add 360 degrees plus 33, right?
Yes.
Positive one.
Yes. Now explain why that works.
Well, if you're stopping at 33 degrees and you needed to make another full revolution to arrive at the same place, that would require that you're traveling 360 degrees, and then you add the 33 so that you can stay at the same terminal, right?
Yes. 100% correct. What happens when I spin 360 degrees? Landing in the same spot, right? So it's an easy way to find coterminal angles. Just add 360. Can you subtract 360? I spun this way. Spin this way. Still land in the same spot, right? I rotated this way first. Then I rotated this way. Still facing you. So you suggest adding 360 to 33 to find one of the positive ones. What does this give us? 393 degrees? That's one of them. Well, now what? You found one. Where's the other ones? Remember when I did that 360 roundhouse kick? It was a sorry 360 roundhouse kick. First of all, my glasses started flying out my face, and then I was clamped up in this room. Of course, you should be able to pull that technique off against an opponent anytime, even if you're cramped, but come on now.
Would you be able to add two revolutions to that?
Yeah, you got the hint. I spun twice and landed in the same spot, didn't I? So I could add 360 and add another 360, and it still lands in the same spot, right? So this is one of them, but we can get another one by adding 360 to this 393. Make sense? Very good. Once you understand the definitions, then the problems and the solutions make more sense, right? You get what we're talking about. You're not just mindlessly calculating. You're not just mindlessly adding numbers like, oh, I hope this works out. Let me do this and that. No, you know why you're doing what you're doing. You get why you're doing what you're doing. And you know what? That's just so satisfying. $360 plus 393 gives me 753. So here's the other positive one. What about the negative ones?
Couldn't you just do the opposite?
Yeah. So what is your suggestion?
Negative 360 degrees
To what?
to the initial.
33 degrees?
Yeah.
Correct. Take 33 degrees and add a negative 360 degrees, if you will. This is just like subtracting it. It is exactly like subtracting it. And you get negative 327. This is one of them. Now what? You just do it again. And you get another one. Negative 687. Make sense? Math didn't seem so sweet before, did it? Math didn't seem so cool before, did it? The right answer is yes. Math is really cool. How many times can we actually theoretically get away with doing this?
As many times as we want, right?
Correct. An infinite amount of times. You could get an infinite amount of coterminal angles. Because the rotations all lie on a circle, and you're always going in circles, so you're just going to stay there. So you can rotate on a circle an infinite amount of times, and you'll still stay there. You'll stay on the circle. Now let's talk about special triangles. We talked about special angles like acute, right, obtuse. This is going to be along the same lines here. We call this kind of a triangle a right triangle. These triangles are really cool and special. But why are they called right triangles?
Because they have a 90-degree angle.
That's it. That's why. Who here could regurgitate mindlessly to me the Pythagorean Theorem? I will note that your book accurately highlights that there was evidence that the Mesopotamians had invented the Pythagorean Theorem 1,000 years prior to Pythagoras' birth. So it's not really Pythagoras' theorem. Furthermore, Pythagoras kind of stole this from one of his students in his school for geometry. So it's called the Pythagorean Theorem, but it doesn't really belong to him. But who could regurgitate it for him?
A squared plus B squared plus C squared.
Yeah. A, B, C, A squared plus B squared is equal to C squared. What's this leg called? It's got a special name. Hypotenuse. Does all this stuff sound familiar? Yeah. Okay. That's because this mathematics was invented thousands of years ago. There's modern day mathematics, and it's cool too. And it has a lot of these foundations in it. Mathematics is a subject that builds upon itself. So we'll be using the Pythagorean theorem in trigonometry, guarantee you that. Now, let's talk about other kinds of special triangles. Let's talk about 45, 45, 90. So these triangles are a special kind of right triangle. They're called 45, 45, 90 right triangles. Why is that? Why do you think they're called that?
45 is half of 90, so
Correct. It's half of 90. Well,
Just because both angles are equal to each other.
yeah, the angles in the triangle is 45, 45, and 90. So we call them 45, 45, 90 right triangles. As simple as that. Next, we have another kind of right triangle. And mine all look the same. They're not supposed to look the same. But I'm not an artist, man. Give me a break. I'm a mathematician. But we are also artists. But you know what I mean. Like Leonardo DiCaprio kind of artist. Or wait, I mean Da Vinci. Yeah. Whoever them dudes was back then, painting stuff. Guess there's modern day artists today as well. What do you think these right triangles are called? Yes. (30, 60, 90 right triangles. Now, I will derive a relation between the legs A, B, and C of this kind of a triangle. Then I will give you what your homework is for this section. And then peace out. Your homework is due when you get back. Next day of class, which is when? Tuesday? What time? Where? Yeah. So here's a cool assumption. You'll figure out soon enough that angles are related to lengths. The larger the angle, the larger the length on the opposite side. Makes sense, right? The more it opens up, the longer the length will be. The less it opens up, the less the length will be, right? It just makes intuitive sense. So actually, if this is 45 degrees and it makes this length, and this is 45 degrees and it makes that length, what can we say about A and B? Yes, sir. That they are equivalent. So when we apply the Pythagorean Theorem, a squared plus b squared is equal to c squared, that really breaks down to a squared plus a squared. Or I could have easily have said b squared plus b squared. Doesn't matter. But then this corresponds to 2a squared, which means I can solve. Which one do I want to solve for in this derivation? I want to solve for c. So this implies when I take the square root of both sides, I get c is technically plus or minus, but we'll take the positive solution. Square root of 2a squared. And as you may remember or may not remember from pre-calc, the radical can travel across multiplication and division. So this ends up becoming square root of 2a. We're kind of short on time. We'll have 1 minute left. If you don't get this, that's fine. I'll rederive it on Tuesday for you. What I want to do is write this homework up. Your homework will be out of section 1.1. It's 8, 10, 14, 16, 21, 22, 28, 36, 46, 65, 75. Have fun. And if you have questions, let me know. I don't have designated office hours yet, but we'll figure that out. I'm teaching at multiple universities, so I have to figure out what's going on at the other ones before I can establish an office hour time interval. Because my other university jobs have online only. We have in-person up in here, up in the good old SNU. So I'm gonna have to figure out what my office hours are gonna be. there was a attendance sign-in sheet. Please, everybody, make sure you sign that.